All right, so what I have here is a punching bag, 75 kilogram punching bag, all right? And right here, somebody provides a linear impulse. You can tell that by the units that are there, 20 Newton seconds. So they're punching, and we see 1 meter down along the bag. Here's where the punch happens. The bag itself is 1.5 meters, so G is 0.75 meters down. And we have the thickness of the bag here at the bottom. It's generally cylindrical, so that'd be the diameter. All right? So, and we're asked to find the following. Once this is punched, what is immediately after the impact of punching this thing, what is the angular velocity? So this thing, picture it's going to be going like so. So once it's punched, there will be a angular velocity associated with this. And then here's the next question, okay? What is the point at about which the bag appears to rotate? Okay, so where is this coming from? We have a G here, okay? This isn't going to be pure rotation. So G is going to have a definite velocity to this. So we can find a VG, and when we go to do this, we're going to find an omega. Well, if we had a velocity here at G, and we had an omega, well, that means that we could go backwards and find like an instant center. So what this is saying is find the velocity at G and find the omega after impact, and then just divide by R on the take the velocity, divide by R, you get the omega, but find, I didn't say that right. You have, let me just write it down. V equals omega R. So in our work, we're going to find this, and we're going to find that. If we form V over omega, that'll be an R somewhere up here where it'll look like an instant center. That's what they're asking here. All right. So this will have some rotation to it, so we will definitely find mass moment of inertia to be helpful. So if you go back into a table, you would see for a long cylindrical solid object like this, the mass moment of inertia is 1/12 m 3r squared plus h squared, h being this. Okay. So if we, and note the diameter here was 0.5, so that's why you see 3.25 squared. R is 0.25. So here we have our mass moment of inertia for the center of mass. All right. We have an impulse. It means we are going to use momentum. So I can leave that still showing. So first thing I'm going to do is apply linear momentum. All right, so before the punch, everything's just hanging there, not moving. So the initial velocity, hence the initial momentum for the punching bag, center of gravity is 0. And then the impulse, that's what that integral equals, is 20. Well, therefore, mass is 75 kilograms, VG2 in the x. So this was just, and I should actually take note here, the impulse is along the x. That detail was missing. All right. So here's the impulse along the x, equals 75 times VG2. Solve for VG2. So we have the velocity of the center of mass, 0.2667. And now we're asked to come up with the angular velocity. Well, for that, we'll just appeal to angular momentum. All right. So how are we going to do that? So initially, it's just hanging, not moving, so the initial angular momentum is 0. Now here we have sum of all external moments. So let's look at this here. This impulse comes in due to a force coming in. Now it's been integrated with time, so it has units of 20 Newton seconds, but it reflects a force. All right, so what I have here is the sum of all moments. My I I'm taking is at G. So what would be the moment, the integrated moment here? Well, it would simply be 20 Newton seconds times this distance from here up to G. So if G is 0.75 meters down and the punch happens 1 meter down, then the moment arm is 0.25. So here's the moment arm, so we can convert that from a linear impulse, multiply by 0.25, and we get an angular impulse. And looking at it, as it punches relative to G, it's trying to go counterclockwise, so the sign is positive. And that's what we have here. All right, and that'll equal then IG 15.23 times omega 2. Okay, post-impact. Post-impact. All right, so from this we can solve for omega. It's direct. Then, so again, we have velocity, we have omega, and so divide by r, we get this distance d is 0.8125 meters. So that's saying, knowing the velocity of g, go up 0.8125 meters, and so that works out to be, to go up to the top of the bag, we go up 0.75 meters. So this distance b here is how far we have to go above the bag. Okay, 0.0625 meters above the bag will be the place where it appears to be rotating around. So there we have that one. And we have several more problems, but we are nearing the end. Catch you later.